Okay, so now we want to talk about rotational kinematics. I just started a new live stream, and that's going to be on page 55. So give me just a second. Okay. And where are we? Here we go. Okay, so page 55. All right. Now, there's a bunch of definitions on page 55, and oh boy, there's just so much information here, all this stuff here. Maybe I'll try going in a slightly different order than we did earlier today. All right, so you can have this page open, and this may be useful. So I'm going to start with a physical object right here. Oops. Something just fell. All right. So while you're getting that ready, I'll get this board ready. Okay. And now I don't know if you can see this very well. Maybe if I move this back just a little bit and lower it down. There we go. And scoot it this way. Okay. So apologies if you can't see that very well. But this is, oh, whoops, let me go to speaker view. There we go. Now I can see a little better. All right, so the idea here is I've got this object that's free to spin here. There's some point masses. And so let's say we're starting with a basic math problem like this. And maybe just to make it clear, I'm interested in looking at this piece of brass, okay? And let's say it's all the way out here at the end. Let's move this one all the way out here to the end. And let's say it starts here, and this is the standard math angle, theta equals 0. As it moves around, whoops, geez, it hits this thing. So let me move it over here. Okay, there we go. So as this thing is moving around, we might want to describe the angle at which it's located. So if I could, okay, there's the origin right behind there, like this. This is going to be where it starts, and then maybe at some random point later, it's right up about there. Oh boy, this is kind of hard to fit in here. Let me cheat. It's going in this circular path like this, and now I got to get this thing out of the way. Bring that back later, maybe. Okay, but the idea is suppose we've got something moving in a circular path. As it moves in this circular path, this could be some angle theta, or sometimes we'll call it delta theta. This distance that it's traveled would be an arc length, S. And this would be the radius of the circular motion. All right. Now, in this case, the rate at which it moves or the rate at which it rotates has to do with its RPMs, its revolutions per minute. So omega is going to be the angular velocity. All right. And I'm going to say that's a vector right now. That's not always true, but just for now. And then delta theta would be angular displacement. All this is written down, so you don't need to write it down. Whoops, sorry. Okay. Alpha would be the angular acceleration. All right. So whether it's speeding up, slowing down as it rotates, this is how fast it's rotating, and this is how much it's rotated. Those are all different things. Again, how much it's rotated, how fast it's rotating, and this is the change in the rotation rate. So this has units of radians. So this one's going to be in units of radians. This one, and then that's equivalent to revolutions. This one would be radians per second, or sometimes people write it in terms of RPMs, revolutions per minute. And this one's going to be in radians per second squared, and we're going to leave it in radians per second squared. It turns out, why do we have to talk about radians? Well, if we want to use the arc length equation, it turns out arc length, S, is equal to R times delta theta. Now, I'm going to get tired of writing delta theta, but so in a lot of problems, we'll set the initial angle to 0. So sometimes you might see me write S equals R theta. If the initial angle is 0, theta and delta theta are interchangeable. So anyway, just a warning there. All right. So now in this case, if you want this to be true, you can't stick degrees in here. It's not going to work. Think about it. What's all the way around a circle? 360 degrees. Circumference does not equal 360 times radius. It's 2 pi r, right? So clearly this angle has to be in radians. Otherwise our circumference formula and other formulas don't make sense. Furthermore, if we have to do calculus, calculus uses radians, not degrees. So all these relate to radians. So we have to use radians. That's why you see me talking about radians instead of RPMs or revolutions, and radians per second squared here. All right. Now, in this case, this is where things get a little bit tricky. Let me bring this back. All right. Let's move this out of the way. In this case, as I spin this thing, and actually, maybe I'll go even crazier. Hold on. I'm going to show you something here up front. Hold on. This is just a flashlight I found hanging on a piece of string, okay? Now, this here, come on now. If I give you a zoom in on this, I just want to show you what this thing looks like up close. Notice there's different radii here. So I can attach the string at this radius or this inner radius, okay? So now I'm going to put that over here. Okay, I'm going to hang this out of the way so it doesn't hit my object as it's rotating. I'm going to take this and I'm going to wind it up on here. Come on now. Sorry, just don't want to get it tangled. It's better to go slow. Now the idea here, if I bring this up close, you can see that string is wound around the inner radius, okay? Sorry if it's hard to see. Okay. And so now, I better lower it down a little bit. When I let go of this thing, okay, the hanging mass is right here. Maybe I'll lower this down just a bit so you can see it. And then the idea is when I let go of this thing, it's speeding up. Do you see that? It's clearly not going, oh, and now it's slowing down a little bit. And I could even put some friction on here. So we could see you could cause something to speed up or slow down. In chapter 6, most of the time we did everything was going at constant speed. Now we're talking about this object as it speeds up or slows down. And I could even do a simpler case where I just put one of these masses here. You can see it'll go back and forth. It could be positive velocities, negative velocities, speeding up, slowing down, all kinds of things. So I want to point out this. It's moving in a circle. There's got to be an acceleration towards the center. It's speeding up and slowing down. There's got to be an acceleration tangent to this. Okay. And so in this case, trying not to damage house, trying not to trip on face. in this case, we could see that AC is R omega squared. We talked about that in chapter 6. It turns out A tangential is actually equal to not your alpha, it's R alpha. Alpha is fish swimming left, okay? And similarly, we know that the tangential velocity, or sometimes we just call it V, is equal to R omega. The idea is, as this thing is moving around, we could talk about the acceleration towards the center and tangent to the circle if we understand how it's moving and can figure out alpha. Now, this is complicated. One more time. The idea here is, as this thing is moving like this, you can see it. Let me make it more dramatic. Okay. And so notice it's speeding up and slowing down. Pretty soon it'll become quite dramatic here. Look, it's almost stopping as it gets to the top, right? And so the idea here is, what if we want to understand the forces on this mass? Which acceleration should I use? Should I use alpha, AC, or A tangential? Which one of them relates directly to the total force on this mass as it rotates?
E10?
Nope.
AC?
Nope.
I think it's just A.
It's
A total.
Both of them. And that's what I wanted to point out. I was deliberately trying to trick you by not telling you the right answer. So my apologies for being a jerk there. The idea is there's another acceleration we need. A total. A total, if you recall from chapter 6, was something like AC in the negative R hat plus A10 in the theta hat or something like that. Now, we don't usually use this too often, but we do use the magnitude of it. So A total, the magnitude, is going to be the square root of AC, plus A tan in quadrature. Sorry, that's a little low there. Now I want you to notice something. AC has got an R omega squared. Think about the units, meters per second per second. A tan has got meters per second squared. Both are good. They both have an R. And so if you do a little bit of math, you get an R omega squared, and then an R alpha squared. They both have an R squared inside. The R factors out. You get the square root of, I believe it's omega to the 4th plus alpha squared. Whoops, let me get that little bit. There we go. So it turns out, and I see there's a chat. My bad, I'm slow. Plus and minus. I have no idea what that was about, Gonzalo. Was that a question?
The minus sign, like to the left of the square root? Or do we not need it?
Here I'm just getting the magnitude. You're right. Every time we should think about it. However, a magnitude we're expecting to be positive. So that's why I didn't do it in this case. Is that good?
Yeah.
Yes. So in general, always think about it. Good that you're thinking about it. In this case, it's okay to not worry about it because the magnitude should be positive. So that's why I use the positive root here instead of the plus or minus. Good question. All right. Others? All right. So now check this out. There's going to be angular kinematics equations, and we're going to have translational kinematic equations. So think about this. I could talk about the rate at which this thing is rotating in terms of its angle. So I could talk about theta here. Theta with negative, okay? And so, or I could literally talk about the distance it has traveled, the arc length. You could talk about the angle it moves or the arc through which it travels. So we can talk about let me do a screen share. All this crap. If you want to, we could analyze the motion of this. Do you recognize these equations right here? What do these look like?
Normal kinematics.
Normal kinematics. Now, I'm going to be a little spicy here. A spicy meatball. I'm going to slide down just a little bit here. Look at, you've got this on your paper, so hopefully you can see it. This equation versus this equation. If you take these rotational kinematics equations, multiply all of them by R, we get back the normal kinematics equations, except we use S and A tangential instead of X and A. So take a second to just kind of look at those equations. If we use this relationship and this and these three relationships, you multiply all of these equations by R, you get back the standard kinematics equations. What we are saying here is when you have a rotating object, you can use kinematics. Now, if it helps, let's just pull one of these up. So I don't have room to put everything in the universe on the whiteboard, so I got to erase somewhere. You've got it all written on the page. All right. So the idea is, oh, go ahead. Yes. And it turns out they both help. You could choose. We'll get to it when we start doing sample problems, you'll see, but they both are useful in different ways. And I'll get to my physical example in a minute, but just for a second, let's start with this. We know that delta X is something like V initial X times time plus 1/2 A sub X T squared. And the idea is what we want to do is get used to thinking, oh, well, this position is now going to angular position. Velocity is now going to angular velocity. And this is omega, not W. You can call it W and I'll be like, no, it's omega. Get used to it. And so you're going to screw up and call it W. W is pointy. Omega is curvy. That's how you could tell the difference. All right. What should I use instead of A if I'm doing rotational variables?
Alpha.
Alpha, fish swimming left. Okay. And then what I'm saying is, if you multiply this times R, this times R, and this term times R, R times delta theta becomes arc length. This, R times this becomes V tangential times T plus 1/2 A tangential times T squared. Those equations can talk about this object. So if I want to know about how much it's actually moving, if I want to talk about how fast it's moving, what letter am I talking about? Let's say I want to know the speed of this thing, this piece of brass. What variable am I asking about?
Alpha?
No.
Omega.
No. I want to know the speed of this thing. Don't overthink it. What speed?
10.
V tan. So watch out. Alpha talks about the rate of change of speed, so it relates to it. Omega relates to the angular speed. So here's something we see. If I don't say the keyword angular in the problem statement, you're supposed to know, oh shit, he means translational variables. If I say the keyword angular in there, okay, got it. So these problems are the same as chapter 2. It's just reading carefully. Did he say angular or not? Did he say AC? Did he say A tan? Did he say A total? Did he say A angular? Reading care, and then you're like, okay, I'll just shove into some equations and crank it out. All right. But so, all right. Now let's take a look, see if there's anything else. And at any time, ask me any questions you want. Okay.
So those bottom ones we call it translational, rotational?
Yeah, they're basically translational as you go around in a circle. Yep.
Gotcha. Okay. Thanks.
And so you're not going in the X direction, you're not going in the Y direction, you're going in the arc length direction this way.
Gotcha. Cool.
Yep. Yeah, cool. All right. Now here's another thing that might not be obvious, but this is actually cool that I have this thing here. I didn't think to do this earlier. So look in this case. I'm going to spin these things. There's two pieces of brass there, right? Are they moving the same speed?
No.
No. Are they moving the same angular speed?
Yes.
Yes. So they have the same rotation rate. They have the same number of RPMs. So this is why the radius matters. Think about that spool here. I don't know if you could see this. Let me bring this up.
Is it because it has more distance to travel?
Exactly. The one that's farther out has more distance to travel, so it's going faster to maintain the same number of RPMs. They have the same number of RPMs because they're clamped to the same rod that's rotating on this wheel. So that's why this radius matters. Now, here's another part that it matters. Remember that this thing has different size radii here. Sorry, let me get out of the way. That's a little hard to see. But right there, you can see the different radii. If you tie the mass onto this string, then this radius relates to the speed of the string. If you tie the string here, this radius relates to the speed of the string, etc. So these radii will help us relate translational variables, things moving in straight lines, to rotational variables, things going in circles. I'm going to show you this one last time just for kicks here. So I'm trying to use this problem to motivate why we should care about this. In a lot of real-world applications, what you want to do is figure out a way to take straight line motion, say of a piston in an engine, and convert it to rotational motion of, say, a camshaft or your wheels as they rotate on the road. Or maybe you want to take rotational motion from a drill and convert it into straight line motion, a screw going into a board. Right? So there's all kinds of applications where we're constantly wanting to convert straight line motion into rotating motion and vice versa. So now here in this case, this is kind of a weird one. Let me just scoot this back a little bit. Let me erase this so we have a flat background. And let me scoot it just a hair this way. Okay, and I'm going to make this balanced because it's pretty unstable. I just want to point this out. This mass is going to fall down and it's going to accelerate, right? If you don't believe me, let's watch it. It's going to fall down. Here we go. So just watch the green mass right here. Do you see it speeding up? I hope you did. Look at this. It's going faster and it's going to hit me in the face. Okay. So the idea here is that mass was accelerating. You could do a free body diagram, tension up, mg down, get its acceleration. From that acceleration, you could divide by r. That would get you the angular acceleration of this. You know the kinematics on this. You could figure out the force on this. And you could figure out if this screw is exerting enough force to keep me from getting hit in the face. All right. That's kind of the big picture of where we want to go with this. I don't know. Does that make any sense at all? Or any questions? That's why we care. This stuff is useful for making practical devices that have one object moving in a straight line, some objects moving, rotating. Let's do some problems. Oh, wait, there is one more thing. The vector nature of this. Technically, these are not vectors. Theta is not a vector. Omega is not a vector. Alpha is not a vector. However, if its rotation remains fixed, we can actually say it is a vector. So I want to be clear on this. Right now, here's the axis of rotation right here, this screw. So in this case, the axis of rotation is not changing. But if I start doing stuff like this, where I do multiple rotations, then this is not the same problem. And there, you can't treat omega as a vector because in this case, it doesn't obey vector mathematics when you rotate it multiple ways and then unrotate it multiple ways. It turns out vector addition, it shouldn't matter if you do A plus B plus C or C plus B plus A. If you do rotational rates, it turns out if you add them in different orders, you do get a different answer. If you don't believe me, rotate a book, rotate it another axis, then flip it, then undo it in different order. The book turns upside down. Okay, so it turns out rotations are not necessarily symmetric. Now, when we're doing this one, I'm just going to go to here. I want to show you one last thing. This thing here. Let's say it's rotating, right? Now, I don't know if you could see this. I'm going to kind of simulate this one. This is the right-hand rule we're going to learn. And I'm going to show you this last bit before we do a problem. If this is the axis, the vector that we are going to use to describe this rotation is not X, it's not Y, it's Z. It's the direction the axis points. And at first, this makes students feel real uncomfortable. You're like, isn't the rotation in here counterclockwise? Yes. If the rotation is counterclockwise, then we say the direction is K hat. And let me show you how this works out by moving this to the side, trying not to kill myself. Let's say this is I hat. This is J hat. And this marker is driving me crazy. All right. Here's my particle. Here's the angle theta or delta theta, however you want to describe it. And let's just assume for right now it's moving this way. So based on that, you could see that it's rotating that way. So that's omega, the direction of rotation. Again, as long as this axis, this would be the axis of rotation, as long as that is fixed, I could treat these as vectors. So now I have angular displacement, angular velocity. Now in this case, I goes to J, goes to K. This direction of rotation is in the K hat, out of the page. Now, if you didn't like this in chapter 3, it's time to start liking it, because we are going to use this for the rest of the semester, where I goes to J goes to K. Always, always, always check your coordinate system. I goes to J goes to K is one correct one. If you recall, dot means out of the page. X means into page. My cheesy way of remembering that was if you're shooting an arrow, okay? If I shoot an arrow at you, the point is coming out to hit you. That's like the dot. If I shoot it away from you, you see the feathers. That's the X. So that's how I remember it. Out of the page is a dot, into the page is an X. So how do you tell which way something's rotating? What you do is curl your fingers the way it's rotating. Your thumb tells you the vector. So in this case, because the axis is out of the page, we say it's rotating K hat. Okay. You could say clockwise, or whoops, you could say counterclockwise, and that would get the point across on a paper and pencil exam. But what are you going to do if you want to do, whoops.
So say in the problem, you say the object is rotating negative K hat. That means it's going clockwise?
Yes. Yes. And then, of course, as physicists, let me show you something here. Hold on. Well, where's my zoom? There we go. What do physicists do? If everything's rotating clockwise, they just change their mind and say, you know what? If everything in a problem is rotating clockwise, I'm just going to go clockwise positive. So it drives students insane, right? But mathematically speaking, that's what we want to use. And now you might be saying, dude, this is stupid. Do I really need to know this? Well, let me see here. I got some problems here. Come on now. Wait, oops. That's center of mass. Let's try this one. The idea here is you're going to code this later. And so to understand this stuff, we need to see, oh, that's kind of cool. And starts getting spatial aliasing. It starts tripping out. Okay, let's stop that now. Okay, just want to point something out. Look at this. We have to use the rotation axis as a vector. So you have to understand this if you're going to do anything useful, right? And if you want to code things somewhere in here, if you want to rotate an object, you have to specify the axis about which you rotate it. So if you want to do anything useful, we need to understand these concepts. That's all it is. Now, you could debate whether or not physics is useful, and I could agree with you sometimes on that one, but that's a separate story. So if you want to do physics, we got to understand it. How about I say it that way? All right, let's do a problem now. Sorry, that's a long intro, but I think it's nice to understand why we're doing this. All right, any questions before we do a problem? Useful conversions, there's your nuggets. If you need some useful nuggets, hertz, that's sometimes used as 1/seconds or revolutions per second or cycles per second there. RPMs, the conversion, here's the conversion. If you need to convert radians per second to RPMs, notice 1 radian per second is about 10 RPMs. Omega, frequency period, revolutions, 2 pi radians, things like that. If theta initials 0, we're going to drop the delta. All right, let's do it. Okay, 10.1. Let's not overthink it. A record player is initially rotating at this. What is that? What did I just tell you in the problem? Is it acceleration? Omega
times R.
Initial. It's initially. You see what I'm saying there? You got it, Jake?
Yeah, gotcha.
Yeah. So that's the initial rotation rate. And we could convert this from RPMs to radians per second. The answer for that, I believe, okay, take a guess. Is it going to be about 300 or is it going to be about 3?
3.
3. And I think it turns out to be 3.491 using that conversion factor, radians per second. Okay. So I just did the conversion that we just looked at. If you need to see it, that's in the solution. Okay. Hey, this one, that's not too bad. That's just the radius. I got that. This is just the time. Okay. So we've got some stuff. What are we supposed to figure out in part A? What variable is that?
The alpha?
Alpha, fish swimming left. And it says magnitude, so we should stick an absolute value on it. All right. What's next? Part B. What are we supposed to get?
Alpha.
A total.
A total. What is a total? Is it AC, a tan, alpha?
It's both AC and A tan, but
that's right.
Square rooted, squared.
Yeah, we call that adding them in quadrature if you care. So when you add things together, similar to the Pythagorean theorem, that's called adding in quadrature. So notice when we did error calculations that one week where lab week was hell. Oh wait, that's every week. I forget. But yeah, that was adding errors in quadrature. All right, anyways. So yeah, that's how we go. So that's that. And then total distance traveled. What is that asking about? Just underlining that.
S? Arc length?
Yeah, S, arc length. Nice. Okay, so what procedure would you follow? If you want to attack this problem, what procedure should we follow? Don't tell me what the answer is. Tell me what you might do. It's okay to be wrong too.
Can we do like the angular kinematics and then change it to the translational?
Sure, that sounds great. What's the first step when you do an angular kinematics problem, if you had to guess?
List your knowns and unknowns.
List your crap. All right. And so take a look. Whoa. That's not what we want. List your crap. Now there's an extra term down here, the radius, right? Okay, so, oh yeah. So notice here's omega final. Here's the kinematics equation. Plug in the 0. I should have plugged in omega final is equal to 0. Should have plugged that in first. Notice we get a negative number, but because I asked for the magnitude, I got to do a positive. Now, got it. So if you want, we could just kind of look at this. What is this one? 10.1, right? 10.1. You're going to make a list. Theta, delta theta, whatever you want to call it. Omega initial, omega final. Here it was 0 because it comes to rest. Here, this was 3.491 radians per second because we did the conversion. You don't always have to convert it, but sometimes you do. Most times. This one was I don't know. Alpha was I don't know. And T was 10 seconds. So we got it. After that, we write our equations. So I know there's the delta theta equation. I know there's the omega final squared equation. And I know there's the omega final equals omega initial plus alpha t equation. I look at this one because I'm like, I know that this is 0. I know this number. I know this number. I can figure that one out. So then I plug in my crap. I do the work. I find the answer. I reread the question. It says to get the magnitude. So then you get the magnitude and do the absolute value. All right. So far, so good. Part B. So this was all part A. Part B. In part B, what are we supposed to do? Total Excel or something? Or what? Okay, total acceleration, right? So GSauce was saying a total is equal to the square root of a c squared plus a tan squared, which I could see, that's not going to help me out too much. So I'm going to rewrite these in terms of the rotational variables. And that's when I get this r equals square root or times square, omega squared, which is omega to the 4th. And again, you could either read this in the book or work it out, derive it. You could plug it in. You got to remember to square it. So you get omega squared and bringing out the r, it's square respect. Yeah, okay. Now, so what do? Which omega do I grab for part B?
The one converted to radians per second?
Nope. Neither one of these. Read the question carefully. Oh, that sneaky Jorstad.
Oh, so it's at t equals 8.
It's at it's at 2 seconds. Oh my gosh, I tricked myself. It's 2 seconds before it comes to rest. I was going to say 2 seconds, but yeah, it's actually at 8 seconds, right? Oh my gosh. So now what do we have to do? Make a new set. We got delta theta equals omega initial. We've got that still. Omega final, we don't know that. We've got alpha. We do know that now because this we figured out from part A. Omega initial was given. We don't know this. We don't know this. But now the time we do know is 8.00 seconds. So what do we have to do? Do angular kinematics, figure out this omega, then shove that in, and then we've got it. So it's not rocket science. That was chapter 9. This is just kinematics, but as you know from chapter 2, it can be tricky. So it should not be underestimated. Let's go back in there. So that will get this job done. Let's take a look and see what I did in the solutions here. Okay. Oh, gosh. Yeah. Oh, okay. So maybe you're clever and take a ratio, but whatever. So there we go. Okay. So now that's great. Now take a look here. I want the total distance traveled. Now, Jesse, I think, was the one that said this was arc length. So I'm going to pick on you, Jesse. It's okay if you make any mistakes. How would you approach part C, Jesse? What do you think? In particular, could I use this table from part A? Would I need to use the table from part B? What do you think? Or would I need to make a new one?
Couldn't you use the first table?
Absolutely.
The full 10 seconds.
Absolutely. And so how would you approach it, Jesse? What did you say we were trying to figure out? Do you remember?
S.
So now I'm going to erase part B here, right? Because we're going to now change this to part C. We're looking for S. How would you do it? There's many correct ways. What do you think you would try?
First, S equals R delta theta.
Mm-hmm.
So can we solve for delta theta? And we already know R, so.
Perfect. Got it? So the idea is, well, now that we know alpha and we know omega initial, and I know time, I could get delta theta. We know R. Got it. Wait, could I do it a different way? Somebody else. Is there another kinematics equation I could have used?
What about omega final is equal to omega initial plus alpha t?
Does that have delta theta in it?
Yeah, if you rearrange the wait, no.
No. So that wouldn't work. What do I put over here?
2 alpha.
The units don't match. This is radians squared per second squared. This is radians squared per second squared. This is radians per second squared times, what do I need?
Theta.
That's the other one you could use. You know this, now we know this. You could get it. So there's a couple of different ways you could do it. Another thing you could do is you could use this one to check your answer to make yourself feel good. All right. Again, all of this crap is talking about essentially this. It's not exactly the same, but it's very similar. The radius is about the same. So if you look at a record player, it's probably spinning about maybe that fast, right? So think about it. 33 1/3 RPMs. What does that mean? 33 revolutions per minute. Let's get lazy and call that 30 so I can round. 30 revolutions per minute. How long should one revolution take?
2 seconds.
One banana, two. Yeah, sure, close enough. I can't, it's like tripping me out looking at this because the pieces of brass look the same. But the idea is it's about like this. This is a record player. It's about the right size. So I love mine. This is a record player. 2 brass masses spinning in a circle, whatever. But you get the idea. This is, and so we're talking about the forces on this. Now, if you want to see something crazy, you could try and, there's probably something on YouTube. Some of you could probably find it faster than me. But if you ever spin a record too fast, if you just clamp it down and put it on a drill and spin it, right, it'll shatter and explode outwards because the molecular forces between the pieces of a record are not strong enough to produce enough force towards the center to keep it moving in circular motion. So if you spin something too fast, the molecules can't produce enough force to give you AC adequate to keep it in circular motion. The thing disintegrates. there's all kinds of applications of these flywheels. I read the other day by chance, they're trying to do this in Formula One cars now. Whereas you slow down in a turn, what they're going to try and do is have you speed up a flywheel, and then as you come out of the turn, have it unspeed up. But now you want to have a small flywheel, so you want to have it be low mass. So it's got to be spinning really fast. If that thing, man, these things are crazy, and they're basically like bombs if you get them spinning fast enough. Because if they go too fast, they just, oh, thanks, Alonso. So there it is if you want to check this out. And I'll let you guys check that out after class or something, or right now if I'm too boring. Either way, you just do what you got to do. You know what I'm saying? Thanks, Alonso. All right. So in this case, let's get back into another problem now. Or we're ready for the next one. Any questions?
Yeah, before moving on.
Yeah.
So I was able to follow everything. I just don't understand how you got 3.491 or omega initial.
Yeah. Let's, sorry, I glossed over that. Let me do it.
Because if you're saying 33 1/3, isn't that 33.3333?
Yes. And so, I didn't show that anywhere. All right. So let's do this. Sorry. Let me do one last step. I should have done that and I forgot. Thank you for calling me on it. All right. So one way you could do it is, what's the fastest way to convert that? Starts with G, ends with Oogle.
Google.
Yeah, boy. But we could also do it this way. It was 33.333, let's say, revolutions per minute. And it's important that we do this because you got to know how to do this basically to know what the computer's doing. Now I know 1 revolution equals 2 pi radians, right? And I also know 1 minute is 60 seconds. Chapter 1. Let's hit it. So what do you want to put in here, on top or on bottom? Let's work on the revolutions. What do I need to put on top and on bottom to get rid of the revolutions?
2 pi rad on top, 1 rev on the bottom.
Yep. And then the next part would be
1 minute on top and 60 seconds on the bottom.
Yep. And then take a look here. I'm going to be really lazy. Do you agree this is approximately 6? 2 times 3.1. 6.28, but it's basically 6 over 60. So we need to divide by 10, and that's why it's going to be about 3. Now, I'm going to tell you this right now. If you don't remember this, it will bite you sometime, usually converting the other way. Okay, so if you convert the other way in your calculator, imagine if we were converting from radians per second to revolutions per minute. You'd have radians, and by the way, this is how you, so that's how you get the answer that you asked about. Are you okay with that?
Yeah, thank you.
So you punch it in and you get it. So now, but what if we had 3.4 radians per second, and I think, let's just say 3.5 radians per second, and I want to convert this to revolutions per minute. Well, what do we get? We got 2 pi radians is 1 rev. And then we also have 60 seconds equals 1 minute. And what have I seen hundreds of thousands of times by this point? People forget to put parentheses around the 2 pi in their calculator. So they divide by 2, multiply by pi, and then multiply by 60, and don't have the sense to check. It should be about 10 different. And so that's why I'm telling you this, because you are going to do it too. I have done it myself and gotten frustrated too. So what you have to do is, if we've got this trick, you know, this should be 60 over about 6. It should be about 35. If you don't get a number that's close to 35, check your pi. See if you forgot parentheses in your calculator. You know what I'm saying? And then let me catch up on the chat. Let me see. Yeah, engineers. You know, well, here's the deal. These rounding tricks usually work to give you an idea. And I wouldn't say engineers round, I would say physicists round, right? 2 is approximately 1, right? So what's a factor of 2 among friends is an old physics. That's literally an old physics saying. What's a factor of 2 among friends? But yeah. So in this case, the other joke that you're going to hear in lab tomorrow, assume a sphere is a cow. That's an old physics joke. Anyways, physicists assume everything's a sphere, right? The zombie earlier was a sphere. Everything's a sphere. We just draw spheres for everything. All right. Enough on that. Cool. We got 10 minutes. Let's look at a couple of problems here. All right. Believe it or not, does anybody know where this town is? Kaohsiung. That's how you say that.
Thailand.
Nope, not Thailand. Close.
Indonesia. I don't know.
Taiwan, boy. So when I was on sabbatical, I went to Kaohsiung. I have relatives over there. Well, through my domestic partnership or whatever I have. But yeah, anyway, so I have my registered domestic partner, or my baby mama, however you want to call her, has a relative living there. So we moved over there, and I was doing physics problems at a tiny little apartment building with my babies, and they were driving me insane. 2 screaming children while I'm trying to do physics. It was driving me nuts. But I took the train from Central to San Duo, and I thought, this is a perfect physics problem. And so I looked up some numbers later. This is the maximum recommended train acceleration rate if you want to keep your passengers from puking or complaining. Okay, this is about 60 miles an hour, right? Times about 2.2, maybe 50, something in there. And then here's the radius. Now think about this, 200 meters. That's a big turn. That's like 2 football fields, right? So, okay. So this is a large curving arc. And now the idea here is determine the angle through which the train accelerates. How would you attack this? What did I give you? Let's first go through that. What is this number right here?
It's acceleration.
It's some kind of acceleration. Is it A or is it alpha? Look at the units.
A.
It's got to be an A, so it's not an alpha, right? Meters per second squared. Alpha has units of radians per second squared. So we know it's not alpha. Which A is it? A centripetal, a tangential, or a total? Go ahead, Alonzo. Yeah, A tan. That's absolutely right. A tan that's what it's talking about. Your change of speed. So that's the straight up definition of A tan. If you're talking about the rate at which you speed up, that's what A tan means. What is this variable?
V tan.
That's V tan. Obviously, this one's R. So how would you attack this problem? You want to get the angle. What variable do we want to find?
Theta.
Theta or delta theta, however. What would you do?
Would you rotate it so the? Oh, never mind.
Let me ask you this. Would you use rotational kinematics or translational kinematics? What do you think?
Rotational.
And that's what a lot of people say. Take a guess what I would do.
Translational.
Yeah. So I'm trying to show you the tricks. Okay. So you would have gotten it right had you done it your way. But watch this. S equals V tangential times time plus 1/2 A tangential T squared. Wait a minute. We already, let's see. Oh, and then I think we also know V tangential final squared equals V tangential initial squared plus 2 A tangential S. This is the arc. Now watch. We know this, and this. You could get this, and then you know the radius. It's easy to go. Could you have done it the other way? Yes, but you'd have to do more conversions and more mistakes possible. So it's not wrong. It's a great way to do the problem. And it's good that you thought of that. Is that cool? Yeah. And so just like, yeah, so that's what you're saying. Cool. So what is different about this compared to chapter 2? We have more tools. Basically, we have all the equations twice because we can link them with the letter R. And then there's sometimes it's faster to do it in rotation, like the first problem. Sometimes it's better to do it in translation and then convert to angles. All right. And so here, this is where it gets kind of weird. I want to maybe, I don't know. I'm going to let you take a look at the rest of this problem on your own. Or I did this problem. I covered this lecture slightly differently earlier, and I did more of this problem earlier, but I just want to go through some stuff because I'm looking at the time. We only have 4 minutes. Look at this one. Here's a problem where I give you the graph and then I make you figure out the stuff. This is very similar to chapter 2, where there was a problem and you had a graph and you had to figure out stuff from that. Look at this one. What do you notice right away about this omega? Or let me rephrase.
It's a function of time.
It's a function of time. So what kinematics equation should I use to attack this one?
You can't you?
You can't. It's not constant alpha. I was doing a bad job there, but look, this is a constant alpha term, but this one is not. So we have to use calculus, right? So in this problem, you could take derivatives and integrals, just like we did in chapter 2. So if you want to get to theta, you do what? A derivative or an integral?
Integral?
Integral. And what do we always have to watch out for when we integrate these? Initial value. Good. All right, cool. And then, and here, if it doesn't specify otherwise, we're going to assume the initial position is 0 unless otherwise specified, right? So now, what if I want to get the angular acceleration?
Derivative.
Derivative. You got it. How about this one? This is the one where you should be falling apart. This is omega, and the acceleration is a function of omega. What happened when what if I wrote it like this? If I said A was equal to kv squared, and I said figure out v of t. Figure out the velocity is a function of time. Do you remember?
Is this one of those like separation?
Absolutely. Separate the variables. You'd say this is dv dt. You'd get the v's with the v's and the t's with the t's. So alpha is equal to d omega dt, right? And that would equal k omega squared. So you get the omega. Now, okay, got it. Cool. Good job. So this one obviously is probably not the focus of our class, but if you're a physicist, you should do it. Believe it or not, I used to live for a while near Nanze Export Processing Zone Station. Woo! And I would take the train past Oil Refinery Elementary School Station. Very odd stations, but yes. So here you could see, this is an example where you're going to have some straight line kinematics, then some rotational kinematics and straight line, some arc length, I should say, and then more straight lines. So that's cool. Here's another one where you have a plot of alpha. Alpha is a function of time. I get a little unit vector in there. And then another one, here's one with some bad units that you got to deal with: centimeters, milliseconds, RPM. So cool. And I'm asking you about revolutions and things, but that's basically it. If you could do those, we're golden. Now, I'm going to end class with this chart. Okay. We have seen that these things are closely related. There's a few weird equations we memorized. Oops, I forgot a paren. My bad. But it turns out we can actually use this chart to analyze all of them. So this is again I'm looking at page 58, and I know you're tired, but let's look at it very briefly. The idea here is if you use this chart, this was the translational quantity. This is the analogous rotational quantity. X was position. Theta is angular position. Similarly, we talked about V and A. What about mass? Well, there's going to be a new thing. Mass is called inertia. Remember somebody said that early today? Mass is inertia. Moment of inertia is the rotational mass. Notice the vector quantities here are going to be assumed to be vector quantities over here as long as we're rotating about a fixed axis, not multiple axes. Force will change into torque. All of those cover chapter 10. Chapter 11 talks about changing momentum to angular momentum. Let's try this out. Let's learn a new equation. Here it says sum of force equals ma. What is the rotational equivalent? Sum of torque equals what?
Moment of inertia times angular acceleration.
Absolutely. Boom. Now we know a torque equation. Isn't that cool? Now look at this. Watch this. This is the last thing I'll do today. I know it's time to go. Just sorry. I really think this is worth finishing. Whoops, not force. What should I be writing in rotation land?
Torque.
Sum of torque, and the equivalent would be angular momentum. Check this out. If there's no force, momentum is conserved. If there's no torque, what is conserved?
Angular momentum.
Angular momentum. We just learned a new conservation law. You now know the big three laws of physics. I'm stopping. We're done. Whew. You guys tough. But yeah, if you want, I did the answers in the back. So this could kind of help you make sure you understand all this.